Good morning everyone, this is Dr. Hemangos De Harma going to discuss about the partial differential equation and its solution using integrating factor. In our earlier classes we have already discussed about the solution of the differential equation, I mean ordinary differential equation using the integrating factor. Before going to the depth of this topic, let's have some basic idea about the partial differential equations. So a partial differential equation is a differential equation which involves two or more independent variables and an unknown function that is dependent variable, and of course some partial derivatives of the unknown function with respect to the independent variables. Here we are considering f of xy, where f is a function of x and y, as a unknown function, and x and y are of course two independent variables. So any derivative of f can be expressed as the partial derivative of with respect to x and of course the partial derivative with respect to y. So these type of equations are called the partial differential equations. We can write the this type of equations if and only if both x and y are independent parameters or independent variables. So in this talk we are going to discuss about the solution of the partial differential equation using integrating factor. Before going to this, we should have the basic idea of the transport equations. So transport equation is a type of the partial differential equation where we can have the general format of a differential equation as ut plus some constant c ux equal to 0, where ut is the partial derivative of u with respect to t, and ux is equal to partial derivative of u with respect to x. The general solution of the transport type partial differential equation is u xt, as u is a function of x and t, is equal to f of x minus ct, where c is a constant as appearing here. Now our idea will be more clear if we try to solve one example how to use integrating factor to solve the partial differential equations. So we are given one solution, one equation, partial differential equation as this is, where ut plus ux plus 7u equal to 0. So we can note that this differential equation, this partial differential equation is quite different from the transport type partial differential equation by the factor 7u. And also we are given a boundary condition u x at t equal to 0 equal to exponential x. So in step 1 we have to reduce this partial differential equation to transport type partial differential equation using the integrating factor. So as this partial differential equation is differ from the transport type partial differential equation by the factor 7u. So we have to define our integrating factor such that considering this part ux plus 7u equal to 0, or we can also define our integrating factor ut plus 7u equal to 0. For in this case we are considering ux plus 7u equal to 0. So if we do that, our equation will become ux plus u equal to 0, where q equal to 7 in this case. And also we are defining integrating factor such that if equal to exponential integration of q dx equal to 0, as q equal to 7 we are getting exponential 7x equal to 0. This is quite similar as we have already done in terms of ordinary differential equations. Now in step 3 we are going to multiply this integrating factor by our original partial differential equation, that is ux plus ut plus 7u equal to 0, which results exponential 7x ut plus exponential 7x ux plus 7 exponential 7x equal to 0. So these two terms, the later two terms, exponential 7x ux plus 7 exponential 7x, these two terms can be expressed as a partial derivative with respect to x of exponential 7x u of x. and also we have, as x is independent of time t, so the first term can be expressed as a partial derivative of t exponential 7x u plus partial derivative of x exponential 7x equal to 0. So here if we consider some other some parameter v is equal to exponential 7x u, then the equation A becomes vt plus vx equal to 0, which is a partial differential equation, I mean transport type partial differential equation with c equal to 1, and its solution will be v of x equal to f of x minus t as c equal to 1. So we will have v of xt equal to f of x minus t, and we know that v of xt is nothing but exponential 7x u is equal to f of xt. Now this is the solution that we have obtained. Now only the remaining thing is that we have to apply the boundary condition, and we have to find out the f of x of t. So the boundary condition we are given that u x at t equal to 0 equal to exponential x. So putting this boundary condition to equation b, we will get exponential 7x, and in terms of u, in place of u we are putting exponential x is equal to f of x. So f of x equal to exponential 8 of x. So now putting the value of a function f in equation b, we will get this is exponential 7x u equal to exponential 8 x minus t, because here f is a function of x minus t, so we are writing exponential 8 x minus t. So ultimately we will find u is equal to exponential x minus 8 of t. So this is the required solution, that solution. So in this talk we have learned how to use integrating factor to modify or to reduce and partial differential equation to a transport type partial differential equation, and how to obtain the solution out of it. Thank you.